So today we're going to talk about a new concept called heat of formation. And the easiest way to say this is the heat of formation is just the amount of energy involved in forming a compound from its constituent elements in their standard state. So we're talking about constituent elements in their standard state. The enthalpy of a reaction, which is basically the energy associated with the reaction, can be calculated if we know the heats of formation of the compounds in the equation. And then the other thing that you have to be very cognizant of and aware of, the heat of formation of an element is always equal to 0. Okay, so heat of formation of an element is always equal to 0. Very important thing. And then when we calculate the enthalpy of the reaction, it is the sum of all the heat of formations of the products minus the sum of all the heat of formations of the reactants. And this little sign here, the sigma sign, is read as sum of. It's a Greek symbol for sum, Greek sigma for sum. So you sum it up. So the sum would be like A plus B plus C. All those added together would be the sum of that material. Okay, so once we can do all that, if we know all that, we can get the heat of enthalpy, the enthalpy of the reaction. Okay, so here are the standard HF formations. So this is the HF0 values of delta HF0 values of many substances that we normally use, and this is at standard state, so this is at 298 degree K, right? And what we're seeing here is that the energy associated with forming carbon monoxide from its constituent elements is equal to minus 110.5 kilojoules per mole. Carbon dioxide would be minus 393.5. So those are those two entries here, this one and this one. And you can go down the list here, and you can see that most of these are negative. There's a few positive, but most of these are negative, indicating that it's a exothermic reaction. Again, when we do this, the reaction of the materials from in their standard state to this compound. So let's look at an example of how we do this. So we're going to actually calculate the enthalpy for this reaction, and we have 2 moles of carbon monoxide, so that's there, and then 1 mole of oxygen gas and 2 moles of CO2. And so we're actually, what is the energy associated with that reaction? So recall that back from the previous slide, that the H of formation is equal to, of a reaction, is equal to the H formation zeros of all the products. We just put product here, and the sum. Okay, the sum of those minus HF zeros for all the reactants. Okay, so let's look at here real quick. So that's the general equation. So let's erase this to make ourselves a little bit more neat. And so that's how we do this. So first of all, we have to identify the products and reactants in this equation. And the products are, as you know here from doing this, CO2 is our product, and the 2 reactants are CO and O2 gas. Okay, so now we want to put these into the proper spaces into our equation, and we've done that here on this line here, right? So here's our CO2, and if you remember from the chart before, CO2's energy value was minus 393.5, so that's the products. There's only 2 of them. There's only one product, but there are 2 moles of CO2, so I need to multiply it by 2 here, right? Because this is energy. This is an energy per mole. Okay, so now I have my closed brackets, which means I'm done summing everything up, and then I go to my reactant side. And as you can see here, the CO, this is the CO value. And since I have, again, 2 moles of it, right, I need to multiply by 2 that value, because it's energy units per mole. I have 2 moles in this equation, so I need that. And then the last one here is oxygen, and oxygen is an element in its standard state, in the standard state, and therefore its heat of formation is 0. So if you do the math here, you've got minus 787 minus 221, right? Minus 2 times minus 20, minus 2 times minus 110.5 is minus 21, and I'm going to be subtracting it because there's my subtraction. And therefore, it's minus and minus, it's plus, and I should get this answer for my answer. So pretty simple, straightforward if you do that way, and you should not get anything, it should not be that much more difficult than that. Okay, so here's another example, and this one is to calculate the enthalpy of a reaction between calcium carbonate, the decomposition of calcium carbonate into calcium oxide and CO2. So the other thing too, as I forgot to mention before, is we always want to check that our equations are balanced. So we want to just put check balance, right? Because if the equation is not balanced, then we can't do anything with it. So check for balanced equation. And so let's do that real quick here. So we have one calcium ion on one side, one calcium ion on the other side. We have one carbon atom on one side, one carbon atom on the other side. And we have 3 oxygen atoms on one side and 3 oxygen atoms on the other side. So the balance checks. Okay, so now we want to set up our general equation. I'll just write that down right here. HF, the delta HF, the delta H, delta H is going to equal the sum of all the products. So let's just put HF0 products and just put that as a PR minus the sum of HFFs, some reactants, right? And so that's our general equation. All right, so now let's plug in some values up here. So let's see where we got here. So let's use a different color pen. So I have one reactant, so that's going to be here. So here's my one reactant, and I only have 1 mole of it. So this is my value for this one here, and that looks good. And I only have 1 mole of it, so there you go. And then in the second one here, we're going to use a different color pen. So the second one, we have calcium oxide, right? And then CO2. We already know what CO2 is. We've done that. So calcium oxide goes here. And then the CO2 one is this one here. And we have 1 mole of each. So therefore, it's 1 times minus 635.1 kilojoules per mole plus 1 times minus 393.5 kilojoules per mole. So that equals minus 102.8 kilojoules per mole. And on the other side, we have 1 times minus 1207, which is a minus 1207. But we're going to be subtracting that from that. So subtracting a minus from a minus. And therefore, we should get this equation here, which gives us this answer here. So that's pretty easy. Should be pretty straightforward how I walk through that one. Okay, here's our last practice problem. You're going to calculate the enthalpy for the reaction 2 moles of nitrous oxide plus oxygen gas gives me 2 moles of nitrogen dioxide. And so make sure you have your equation balanced, and it looks like it is. So our equation balanced, we have 2 moles of nitrogen, 2 moles of nitrogen, that checks. And then we have a total of 4 moles of oxygen. We have 4 moles of oxygen. So that checks. And then the other thing we want to make sure is that we account for the coefficients here. So here's our coefficient of 2, and here's our coefficient of 2, and make sure that they account for in the reaction. And the last thing to remember is that the oxygen gas is going to be a 0 energy because it is a element in its standard state. And then finally, when you report the energy, you're going to just report it into kilojoules or some type of energy unit for this particular equation. It's never kilojoules per mole because we're calculating the total energy of the equation. And so it's just going to be total energy units, right? And so those are the tricky things around. So set this up and see if you get the same answer that I did here. Okay, here are the concept learnings that hopefully the student took away from the lesson video. The enthalpy of a reaction can be calculated using a balanced equation and knowing the HF formations of the products and reactants. Remember, the HF formation values are the energies associated with forming the compound from its constituent elements in their standard state. Most HF values are known already and can be looked up for most chemicals. To calculate the enthalpy of the reaction, the enthalpy is determined by summing all the HF zeros of the products here and then subtracting them from the sum of all the HF zeros from the reactants. And when you do that, you get the enthalpy of the reaction. To make sure you understand that you have to use stoichiometry in the balanced equation to properly calculate the energy, I've given you a little bit of an illustration here to recall. We have a balanced equation here of 2A plus 3B gives me 1 mole of C plus 2 moles of D. When I do the enthalpy of reaction equation, I must make sure that I use the coefficients in front of each one of the compounds, for example A, to make sure that I multiply that coefficient by the energy associated with the formation of A. Because the energy of formation of A is given in energy units per mole. So for example, joules per mole or calories per mole. So joules per mole, and if I have 2 moles of the material in the chemical equation or in the balanced equation, I need to multiply the energy level by 2. Same thing for letter B, compound B. I have 3 here, and therefore I need to make sure that I have my 3 times the heat of formation of B in the equation. And the rest of that applies to both A and D. C is only 1 mole, so therefore you don't have to multiply it by anything except for number 1. So hopefully this lesson was useful to you. You should practice on some of the equations or problems that I've given you elsewhere.